everyone. In today's lecture, we'll be discussing the basics for studying the Lyapunov-Second method. And in this part, we'll be discussing the sign definiteness of the scalar function and Sylvester theorem. So, why scalar function? Because the energy we are considering for the system is basically scalar function and also positive. Why we need to study this topic? Because most of the time it is difficult to find the scalar function or the energy function for the system. So this topic is very important to find the energy of the system. And also in the Sylvester theorem will be coming up the concept which will help us to find the positive definite function. Basically, the energy function for the system are basically scalar and also positive. So how we can come up with that positive definite function, the Sylvester theorem can help us. So first part is sign definiteness. So here, we'll come up with positive definiteness. And let's assume we have the function v of x, which is we can write also v x1, x2, dot, 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 xn. So if the function is defined for n states, and if it is positive definite, so v of x will be positive for any in the state space for any value of x. So we can say for any value of x which is not equal to 0. And if it is 0 if x equal to 0. If the function satisfies this condition, we can say the function is positive definite. And second part, positive semi-definite, positive semi-definiteness. So here the Vx, this Vx will be positive in the state space for any value of x except one or more points in the state space including the origin x equal to 0, where Vx will be 0. So we can write Vx will be positive, it will be positive for any state in the state space except some points or more points and x equal to 0, which belongs to xn, this Vx will be 0. So it means it will be, you can write here, let me write here, Vx x1 x2 dot 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 xn is said to be positive at all points in the state space except one or more points in state space including the origin x equal to 0. So where Vx will be 0. So once the function follows this definition, we can say the function is positive semi-definiteness. Now third part is negative definiteness. So here the function v of x is a scalar function and it will be negative for all x not equal to 0. and 0 at x equal to 0. If the function follows this rule, then you can say the function is negative definiteness. And third is negative semi-definiteness. So here actually we can come up the same definition what you have proposed here. The Vx will be the Vx said to be positive. Instead of positive here we'll say negative at all points in the state space except one or more points in the state space including x equal to 0, Vx equal to 0. So it is same definition except this instead of positive we will write negative. So I'm not going to do that. So now this is how we can define the negative definiteness, positive definiteness. Now we'll come up some, we'll consider a quadratic function and which can define the total energy of the system. So let me write. Basically, the most of the system, what you see in practically now in daily life, the dynamical system, the total energy can be defined by the quadratic formula. So we can write the total energy for, for a dynamical system can be defined in a quadratic form as v of x equal to I equal to 1 to n and j equal to 1 to n. So we can write ki is j, xi and xj. Where ki is j, we can say real constant, some constant parameter, write real constant. So as I have to say that most commonly used quadratic function in a matrix form, we can write v of x, can write the most. So I hope it is clear. So here basically most of the energy of the system we can define into this form. How we can write in this form we'll explain now. So the most commonly used quadratic function in a matrix form. So we can write Vx, can write equal to x transpose Qx. So now if you notice here, this Q is very important here. So based on Q, we can comment the if Vx is positive definite or not. So here, okay, let me do it, then I'll come up some simple example and explain. So here, where Q equal to, we can come some matrix, we can get some matrix Q11, Q12 dot dot dot, Q1n, Q21, Q22, Q2n, and Qn1, Qnn. So this is the matrix. And here X transpose is nothing but X1, X2, Xn. So here we can write V of X, X transpose Qx. We can substitute here X transpose X, X1, xn into this Q matrix, which is defined by this into x, which is x1, xn, right? And from this, we can write Q11 x1 squared plus Q22 x2 squared Qnn xn squared plus Q12 Q21 x1 x2 plus Q13 plus 31 x1 x3 plus Qij plus Qji xi xj. So we can get this expression. So now if you take the simple example, for example, we have the function Vx equal to x1 square plus x2 square. So we can write x1, x2 into 1001 into x1, x2. So we can write in this form. So this is, if you notice carefully, this is the scalar function and also positive. So we can consider this the energy of the sum system, which can also define in this form, where this matrix is positive different matrix. And so the most important thing is how to find this matrix, and based on which you can find the total energy of the system. So now, from this we can write Qij equal to Kij when I equal to j, and half Kij plus Kji Qji when I not equal to j. So now, how we can extend this concept for an example? So I hope this theory is clear. Now let Vx some function for x1 square plus 2x2 square plus 2x1 x2 plus x2 x3 and plus 2x1 x3. Now if you compare this equation, this is equation number 1, for example, this is 2. Now if you compare both this equation, we can write here K11 equal to 4, K22 equal to 2, K33 equal to 2. I'm missing one term here. Here another term is this is x3 square. Okay. And K33, actually K33 is here. 2x2 square plus x3 square plus 2x1 x2. So here we can write this is 1. K33 1 and K23 equal to 1 and K23 and K I can write and K13 equal to 2. Now if you compare this case with Q1, Q2 like that. So we can write here Q11 equal to Q11 equal to 4, Q22 equal to K22 equal to 2, and Q33 K33 equal to 1. And Q12 we can write half K12 plus K21, which is here K21 is 0. So this is basically 0. So we can write half K12, and K12 actually we are having 2. So 1, 2 into 2 equal to 1. And similarly, Q23, sorry, 23, half we can write K23 plus K32. So K32 here is 0. So we can write half K23, and K23 is 1, half into 1. Half. So now we can find, again, we can find K13, which is half K13 plus K31, and K31 is 0 here. So we can write it is K13 is 2. So we can write 1. And this is also we can write K31. Okay. So based on these Qs, we can form the Q matrix, which is Q equal to 4, 1, 1, 1, 2, half, and 1, half. So this is, if you notice, this is basically our positive definite matrix. And we can write now Vx equal to X transpose Qx. Now, if you use this if you use this matrix, and if you multiply this matrix with X transpose pre-multiply and X with post-multiply, we can get this Lyapunov function. So this is how we can find the Lyapunov function. But the most important part is how to find this positive definite matrix. Now we'll use the Sylvester theorem, how to find this positive definite matrix. So here, positive definiteness. So now we are doing the second part of this in this lecture, positive definiteness. So a quadratic function v of x equal to X transpose Qx is positive definite if and only if all the principal determinants which is we can define Q1, Q2, Qn, but out of this we'll explain now. Just let me wind up this definition of the matrix Q are positive. Here, if you let us assume we have the matrix Q, and if it is defined by A, B, C, D, E, F, G, H, I, for example, this is the matrix, and from this matrix we can form Q1 as Q1 is basically A, and Q2 we can form as A, B, and D, E. Basically, this one, this matrix, and Q3 we can form as the whole one, A, B, C, D, E, F, G, H, and I. So this is basically the third principal determinants. Now, we'll look something, sign definiteness. Okay, it is actually we can just simply go the example. I think it is better instead of this. So example, uh, let us consider we have the some function v of x equal to x1, x2, x3, and we have the matrix for the same matrix what you have done, what you have obtained here, the same matrix I'm assuming here, and we'll check the positive difference for this particular case using this Sylvester theorem. Okay, so here 412 we have the first row, and second row we have 1, 2, half, and third row 1, half, and 1, and we have the x vector x1, x2 dot dot, sorry, just simply x3. Okay, so from this we'll find q1. So q1 is here 4, and q2 we can form the matrix, the determinant of a matrix 4, 1, 1, 2. And if we take the determinant of this, it will be 8 minus 1. So it is greater than 0. And similarly, if you take the whole matrix determinant, which is 4, 1, 1, 1, 2, half, 1, half, 1, and this is 5. So we can say that all the principal determinants are positive, and we can say this is positive definite function. Okay. So this is how we can find the Vx function, and also if you need to find the matrix inside this Q matrix, we can also follow the same procedure what you have done before. So this is very important for understanding the second theorem, and we'll be using this kind of function in our example what we'll be taking later. And also it is very important that the structure of the Lyapunov function for a in-Tholar system, how to choose. Sometimes it is difficult to choose the Lyapunov function, but if you know the how to find the positive definite matrix, and we can find. Anyways, we'll have the lot of example in the later lecture, and also how to find the Lyapunov function for any other dynamical system. We'll go through in detail. So let's stop it here. We'll continue from the next lecture.